Okay, so in the last video we talked about the basics of what makes up a circuit, and we also talked about the concepts of voltage and current and Ohm's law, that V equals IR equation, that's called Ohm's law, and we did some basic calculations with Ohm's law. Okay, and so in this video we're going to talk about the resistance of a wire and then do calculations with what's called power dissipation, which is basically the power used up by an object in a circuit. Okay, so when you're talking about um, the resistance of a wire, think like a like a metal wire, just like you see here in the picture. There's basically a few different factors that could affect the electric resistance of a wire. Okay, and I know on this slide it talks about the two primary factors. The third primary factor that's not mentioned here is basically the material making up the wire. Okay, and some materials have different resistances than others, um, but most wires that you find inside your walls are made of copper because copper is really cheap um, to use. And so besides the material, there's two primary factors that affect the resistance of a wire. Okay, and that is the length of the wire. And the second factor is what's called the cross-sectional area of the wire, which is basically just a fancy way of saying the thickness of the wire. Okay, and so aside from the material that the wire is made of, those are the two primary factors that affect resistance. Now, as far as length goes, basically, in simple terms, the longer the wire is, the higher the resistance. And so remember, electric resistance basically indicates how easy it is for current to flow in a circuit. And so when you talk about resistance, the more resistance you have, the more difficult it is for current to flow. And so if you have a wire that's longer, because it's longer, it's more difficult for those electrons to flow through the circuit. The longer the wire is, the more resistance it has. And likewise, cross-sectional area, like I said, is a fancy way of saying the thickness of the wire. And so the thicker the wire is, the lower the resistance. And if you imagine it like a pipe and water flowing through a pipe, that kind of makes sense, right? Because if you have a bigger pipe around, it's more easy for stuff to flow through because it's a wider space. And so the thicker a wire is, the lower the resistance is, meaning that it's more easy for charge to flow, for electrons to flow. Okay, and so I'm going to show you a simulation. Okay, and so basically what I want you to see from this simulation is that this is a piece of wire, and here's a resistance. Over here right now it says 0.667 ohms. Ignore what the equation means. Basically you can see as it gets longer, the resistance increases. As the cross-sectional area, aka the thickness, gets bigger, the resistance decreases. Okay, so shorter, longer. Okay, thinner means bigger resistance because it's more difficult for the electrons to flow. And then thicker means less resistance because it's easier for the electrons to flow. Okay, so those are the factors that affect the electric resistance of a wire. So just to do a simple example, here is example 3. And example 3 says the two pieces of metal shown are made out of the same material and have the same length. Which of these, okay, metal A or metal B, do you think will have the greatest resistance? Okay, so try to answer that question on your own. Okay, so the answer to this question is metal B. Metal B is going to have the greater resistance because it has a smaller cross-sectional area, meaning it's more difficult for charge to flow through metal B. Okay, and so the correct answer should definitely be B. Okay, that's going to have the bigger resistance. All right, so now let's move on and talk about electric power. Okay, so when we talk about electric power, we've actually talked about power before. Okay, power we talked about in the energy unit. Power has to do with the rate at which energy is used per second. Okay, so in other words, the unit for power is the watt, and basically 1 watt is 1 joule per second. And so when you're talking about a component or a device in a circuit, that component can use energy every second from the voltage source. And this is what's called power dissipated. And dissipated basically means used up. Okay, so dissipated is like a fancy way of saying used up. So when we talk about the power dissipated by, like, say, a light bulb, we're talking about the rate at which it uses up energy. Okay, the number of joules per second or the number of watts it uses. The power usage for some typical devices are shown on the next slide. And a lot of the time you can either look up this information or it will be located somewhere on the device. Okay, and so just to give you an idea, these are just some like average values. But for example, like your refrigerator probably has a power rating of around 50 watts, which means when you plug your fridge in, it uses about 50 joules per second. Okay, your freezer has a higher power rating because it takes more energy per second to, create the low temperatures of a freezer. Or, your washing machine might have a power rating of 500 watts, meaning it uses 500 joules of energy per second. Okay, or a dishwasher might be 1300 watts. And the reason that's important is, like I talk about on this slide right here, is because that's what your electric bill is based off of, right? How much energy you use, you have to pay a certain number of cents for each for different energy usages. And so when you're shopping for objects, keep in mind the power rating because that could affect how much your electric bill ends up being. And this is just showing, like, this is the back of a computer, and that's just to show you how, like, if you look carefully on a lot of objects, you can actually find the power rating. You can see right there it says 390 watts max, okay, meaning that this can use up to 390 joules per second. Obviously, it could use less. Now, to calculate power, we have some different equations, and the equation you use to calculate power depends on what variables you're given in the problem. Okay, so the power dissipated by a component in a circuit is given by one of these three equations. Now, which equation you use again depends on what you're given in the problem. Okay, so here are the three equations. P is power, okay, that's measured in watts. Remember, I is current, V is voltage, and R is resistance. We talked about all of those variables in the last video. Okay, so we have P equals I times V, P equals I squared times R, and then P equals V squared divided by R. So make sure you have those equations added to your notes so you can use them to solve some problems on the next few slides. Okay, and then this chart basically just shows the four variables we have in this unit: power, current, voltage, and resistance. It shows you the symbol for each of those, the unit for each of those, and then what the unit symbol is. Okay, so for example, remember the way we write ohm is with the Greek letter omega that looks like a horseshoe. Okay, so you should already have all of this in your notes, but in case you don't, you might want to add that. Okay, so now let's do some basic calculations with power. Okay, so example 4 says a 60-watt light bulb is plugged into a wall socket that has a voltage of 120 volts. In this country, by the way, our power outlets have a voltage of 120 volts. And if you need less than 120 volts, then what you need is you need like a little device called a converter that basically takes the 120 volts and decreases it to a smaller amount. So if you've ever used like a phone charger, for example, it has like a little cube that you plug into the wall, and then you plug the cable into that little cube. The purpose of the little cube is to decrease the voltage from the wall from 120 volts to like 10 to 15 volts, I think. Okay, so next time you're charging your phone, take a look at what it says on the charger, and it'll actually say the voltage on that little cube. Okay, but basically it's taking the 120 volts from the wall and making it to a smaller number, so you don't blow up your phone. Anyway, so example 4, we have 60 watts. Remember, watt is the unit for power, so this is the power of the light bulb, and this is the voltage, 120 volts, so that's V. And the first question says calculate the current that flows through this light bulb. Okay, so we want to look at our equations. We know that current is I, and so we want the equation that has P, I, and V. And so that's going to be P equals I times V, PIV. We plug in 60 watts for P. I is the unknown. V is 120. 120 is multiplying I, and so we want to divide both sides by 120. Okay, and then 60 divided by 120 is 0.5 amperes. Okay, remember capital A for amperes. Okay, so that is the first part of example 4. Now, example 5 then says calculate the resistance of this light bulb. Okay, so remember in the last video we talked about Ohm's law, V equals I times R. And so now that I have I and V, I can use V equals I times R to find the resistance. Because I have V, which is 120. I now have I, which is 0.5. And so to find R, all I need to do is divide both sides by 0.5. Now I also want to point out that I could have also used one of the power equations that had V and R in it, or I and R in it, but I decided to use Ohm's law instead. So that's going to be 240 ohms is the resistance of this light bulb. Okay, so that is example 4. Pause it there if you need to look at that some more. Okay, example 5. Okay, so example 5 says a simple circuit is created as shown to the right. First question says calculate the power that will be dissipated by this resistor. Okay, so look at what you're given in the picture. Figure out which power equation to use, which are the power equations you need to use. Just to show you them one more time. Okay, pause this here if you need to write those down. Okay, and then looking at this equation, what you're given, I want you to try to do example 5 on your own and calculate the power dissipated by the resistor, and then I want you to calculate the current that will flow in the circuit. Okay, so try to do that now. Okay, so we have voltage, V, we have the resistance, R. So I want to use a power equation that has V and R. So it's the one that looks like V squared divided by R. That's going to be 9 squared divided by 100, which is going to be 0.81. I was about to say A for ampere, but power is measured in watts. Okay, so 0.81 watts should be your first answer. And the second question says calculate the current that will flow. Now I can use any equation I want that has current. I'm going to use, let's see, V equals I times R. I know V is 9. I don't know I, but I know R is 100. So I can divide both sides by 100 and get I equals 0.09 amperes. Okay, so that is example 5. Pause it there if you need to look at that some more. Okay, and just to do one more quick example. Okay, example 6, we have a 5 ohm resistor. It's connected to a battery. A 2 amperes of current is measured to flow through the resistor. First question says, what is the voltage of the battery? And I'm going to go ahead and do the first part of example 6 for you. I have R and I, and I'm looking for V. So that's just going to be V equals I times R, which is Ohm's law. So 2 times 5 is 10 volts. Now the second question says, how much heat is the resistor creating per second? Okay, remember, heat is measured in joules, and so it's asking for the number of joules per second. In other words, it's asking for the power dissipation. So using one of the 3 power equations we have, I want you to calculate the power dissipated by this resistor. Okay, so try to do that now on your own. Okay, because I have V, R, and I can use any of the power equations. I'm going to use the PIV equation, P equals I times V. I know I is 2, and I know V is 10. So 2 times 10 is 20 watts, or 20 joules per second, and that is the answer to example 6. Okay, so pause it there if you need to look at that some more. Okay, so what have we learned so far in this unit? We talked about the essential elements of a circuit. We talked about what is current, what is voltage, Ohm's law. Remember that's V equals I times R. We talked about electric resistance and the factors that affect the resistance of a wire. And then we've talked about power dissipation. Okay, so those are everything we've talked about so far as circuits go. As always, please let me know if you have any questions, and I'll see you guys in the next video.